Hello and welcome to this video brought to you by Smart Exam Resources. In today's video, I shall explain to you the process of iron extraction. And before doing that, I'm going to explain to you a few facts about iron. And what are those facts? So, the first fact is that iron is found in abundance. So, iron is found in abundance in the Earth's crust. The second thing that you need to know about iron is that it is highly reactive. So it is highly reactive. Another thing is because it is highly reactive, it exists as compounds. So it exists as compounds. And what kind of compounds does it exist? Well, the compounds are, the first compound can be said to be the oxides. So it exists as oxides, and you have hematite as one oxide. So you have the hematite, which is Fe2O3. Then you have the magnetite, which is Fe3O4, and limonite, which is Fe2O3 0.3H2O. Now you need not know limonite for sure, but hematite and magnetite you need to know the names and formula, okay, from the exam point of view. Also about the carbonates. So the second compound that iron exists as is the carbonates, and carbonate is just, I'm giving you one, that is FeCO3. And the third compound that iron exists is, it exists as sulfides. Okay, so the sulfide of iron that is present is the iron pyrite. So you have the iron pyrite, and the formula is FeS2. Okay, so now these are the compounds that iron exists in. Now when you're going to do iron extraction, you're going to separate this iron from its compounds. So you need something that is more reactive than iron. Okay, and for understanding which element is more reactive than iron, we need to have a look at the reactivity series. Okay, so that means we need to know a method. Okay, we need to know which is the method that we are going to use to extract iron from its compounds. And so, like I told you, only a more reactive element will be able to reduce this iron. And so we have to look at the reactivity series. As you can see in the reactivity series, carbon is more reactive than iron, and therefore carbon can reduce iron compounds to iron. So we know the method of iron extraction, which is reduction of iron compounds with the help of carbon. So now let me just jot this down quickly. You can also make a note of it. Okay, second thing, we know the method of iron extraction. Now what we are interested in is what are the raw materials that we'll be needing. Well, the process name I'm going to reveal later. Okay, and even the unit I'm going to show later. So now I'm going to talk about the raw materials. So what are the raw materials? So there'll be three raw materials that I'll be showing here, and the first raw material is going to be the coke. And if you want to know something more about the coke, so you can have a look at the image of the coke, and as you can see to the left of the screen, coke is a fuel. It is obtained by burning coal in the absence of air. It has a high carbon density, so extremely rich in carbon, and it has got very few amounts of impurities. So that's about coke, the first raw material. Now you talk about the second raw material, which is calcium carbonate. And calcium carbonate, why do you need it? Remember, the iron ore, the compound of iron that we are going to use in the iron extraction, is going to come from the Earth's crust. Is definitely going to have a lot of impurities, and the major impurities in the extraction of iron is going to be silicon dioxide, SiO2. So calcium carbonate is going to be used to remove that silicon dioxide. Okay, and the next thing is your main raw material, which is containing iron in it, and that is the iron ore. Now let me tell you a few things about the iron ores, and it is that, like I told you, that Iron is in abundance in the Earth's crust in the form of compounds, and two of the most famous ores that one would like to use in iron extractions would be hematite or iron pyrite because they are in abundance. But if you see iron pyrite, that has got sulfur content in it, and you know sulfur gives out poisonous gases of sulfur dioxide, which is not a welcome thing. So that's the reason in the extraction of iron from its compounds, iron pyrite is not considered. So what you would be considering is hematite, which is iron oxide. Okay, so the iron ore that you'll be considering in the extraction process would be iron oxide. And something more about the iron ores, I'll just show you images about the iron ores I just spoke some time ago. Now the images are because you will not be able to see these in real life around you. You might have to go and visit a place or make a request to get to see these. So these are the images, please have a look. Now, so you know the method of iron extraction, which is reduction of an iron ore with the help of carbon. You know the three raw materials, and I've told you the ore of iron that we are going to use is going to be hematite, which is Fe2O3. Now, having said that, I'm going to show you the apparatus or the industrial unit rather in which the iron extraction takes place, and that unit has got a very special name, which is the blast furnace. Okay, so I'm going to just quickly erase this and I'm going to show you my blast furnace. Now there are different sections of the blast furnace where reactions take place. The regions are hot, some regions are cooler compared to the hotter regions, but not really cool at all. So have a look at the blast furnace, and I'm going to tell you a few things about the blast furnace which you need to remember from the exam point of view. Now this is the place where the charge is put in or where the raw materials are put in. Okay, so R stands for raw materials. This is the place where the exhaust gases come out. So you have the exhaust gases which are coming out. And you know the exhaust gases which are going to come out are going to be carbon monoxide and carbon dioxide. You'll soon get to know how these are formed. Then from these parts you have the blast of hot air coming in, and the temperature of that hot air is somewhere around 550 to 850 degrees Celsius. Okay, that's the temperature of the hot air. Okay, now there are outlets. From this outlet from the upper outlet, what's going to come out is the slag. You'll have slag coming out from the upper outlet, and the lower outlet is going to then allow the molten iron to come out. Okay, so from here what's going to come out is the iron that is collected just below the slag. So always remember that there is the slag that is collecting on top of iron. Okay, and iron is going to collect below the slag because iron is more denser than slag. Okay, so this is what it is. And then again, what is the key concept over here? The key thing over here is that there's a range of temperatures in this section. There's not just one temperature, there's a range of temperatures, and there are different reactions that are taking place in this range of temperatures. Now what I'm going to explain to you is what exactly is happening, what are the reactions taking place at different temperatures. Now to do that, I'm going to take a fresh page. Okay, let me begin by changing my ink color to something which is okay, maybe light. Okay, so you have the first thing that is happening in the lower part of the chamber, which is the combustion chamber. And in the combustion chamber or combustion zone, what is going to happen is your carbon is going to react with oxygen. So you have the carbon which is going to react with oxygen, and it is going to form the carbon dioxide gas. Okay, I'm not writing the state equations, you please make a note of the state equations. Okay, so carbon is going to react with oxygen to form carbon dioxide gas. This reaction is going to be highly exothermic. Exothermic means there's going to be heat that is given off, and when heat is given off, when it started with 550 degrees Celsius to 850 degrees Celsius, the temperature is going to rise from that temperature and is now going to be around, so the temperature is going to increase and it's going to reach around 2200 Kelvin. Okay, so at that temperature what's going to happen? that temperature, whatever carbon dioxide was formed in the first zone. So I'll just change the ink color, that will make it easier. So every stage I'll just use with a different color. So maybe I can just use this color. So when in the first combustion zone the temperature is increasing, and I told you it goes around to 2200 Kelvin. Okay, and then so you got the temperature increases, and what is the reaction that is happening over here? Whatever carbon dioxide was formed in the combustion zone, that is going to further react. Okay, so that carbon dioxide, okay, is going to further react with more carbon to form carbon monoxide. So here you have the carbon monoxide gas formation. Okay, so this is the second thing that is happening, and again when this happens, this reaction is an endothermic reaction. So this reaction being an endothermic reaction, so this is an endothermic reaction. So because of the endothermic nature, the temperature is going to decrease. So on the top, what is going to happen? The temperature will fall now, it won't rise further. So you will have the temperature decreasing. So I'm going to write here the temperature decreases. A downward arrow is shown to show that the temperature is decreasing, and it decreases to 1570 Kelvin. 1570 Kelvin. And what is happening at that temperature? Well, there are two things that are happening at this temperature. The first thing that is going to happen is, I'm talking about 1570 Kelvin, look at the blue color. So the first thing that's going to happen is, if there is any ion that has been formed, listen carefully, any ion that is produced in the upper parts of the furnace is going to melt. So I'm just going to write in short, so it's going to melt. Okay, so iron that is produced in the upper parts of the blast furnace is going to melt. And the second thing that is going to happen is, if there is any Fe2O3 that is present in this part of the chamber where the temperature is 1570 Kelvin, so any Fe2O3 that is present here is going to get reduced into what kind of compounds? Is going to change into iron and carbon monoxide. So it's going to change into iron and carbon monoxide. Okay, so now I've just corrected these two reactions. I had done a wrong balancing for the 2200 Kelvin for carbon monoxide, and I'd forgotten to write that Fe2O3. I just written FeO3. So I've just corrected that. So in case if you've jotted it down, just make the changes. I forgot to, there was some error in the formula for iron oxide that I'd written, which I said I've corrected. Okay, fine. So now this chamber is called as a fusion chamber. Okay, so I'm just making a note of it again. So okay, this is the fusion chamber or the fusion zone. Okay, so you had the combustion zone, then you had the fusion zone. Okay, and then what happens is, so what's happening, just observe the temperature from 550 to 850. It has gone up to 2200 Kelvin. Then from there it has dropped to 1570 Kelvin, and then from there you have these kind of reactions that are happening at 1570 Kelvin. Now what happens further? So as time progresses and when more reactions keep happening, you will find that the temperature drops from 1570 to another temperature, and that temperature is of the slag formation, and that is 1270 Kelvin. So the temperature further drops to 1270 Kelvin, and this is the zone which is the slag formation zone. So you can call it the zone 3, which is the slag formation zone. So slag formation zone. And what happens in the slag formation zone? Well, there are two things that are happening in the slag formation zone. So the first thing that happens in this zone is, if there is a limestone, obviously there's going to be limestone because we have put the limestone. So the limestone that is present there is going to thermally decompose into calcium oxide and carbon dioxide. So calcium oxide plus carbon dioxide, okay, that's going to be formed here. And second thing is, so this calcium oxide is also called as lime. So this calcium oxide is going to react with silicon dioxide SiO2 to form calcium silicate CaSiO3. Okay, and this is nothing but a slag. Okay, so these are the two things that are happening in this slag formation zone. Okay, first is the thermal decomposition of calcium carbonate into calcium oxide and carbon dioxide. Then the calcium oxide or the lime that is formed further reacts with silicon dioxide to form CaSiO3, which is the slag. One of my kids also calls it as the casio, CaSiO, but you put a 3 and it becomes calcium silicate. That's how he remembered, and he told me to share it with other kids whenever I teach. So since I'm teaching you online today, I'm just sharing so you can remember calcium silicate with the word casio, CaSiO. Okay, just put a 3 and it becomes calcium silicate. Fine. So this slag that is formed is actually floating on the part that is above the chamber for the molten iron. Okay, so slag is less dense than iron, so in the blast furnace it will be seen to float above the iron that is formed. Okay, so this is the zone of slag formation. Now what happens after this? So is anything else happening after this? Well, yes, a lot of things are happening after this, and one of the things that keeps happening is a lot of reduction. So there is a reduction zone, so you can call this as your zone 4, which is your reduction zone. So I can say this is my reduction zone here. And what's the temperature of the reduction zone? It is 875 Kelvin. That's the temperature of the reduction zone. So because it's a reduction zone, obviously reduction is happening. So which is the chief reducing agent here? So your chief reducing agent, I'm writing it down for you. So your chief reducing agent is carbon monoxide. Okay, so carbon monoxide that got formed in the second chamber, which is the fusion zone, is going to be our chief reducing agent. And what's going to happen is all oxides of iron are going to be reduced by this carbon monoxide in this chamber. So I'm going to write down the oxides of carbon, and the first oxide I can think of is the iron oxide, which is FeO. That's going to be reduced by carbon monoxide, and the product is going to be iron, which is Fe plus CO2. Now the next one is 3Fe2O3. 3Fe2O3 is going to then combine with carbon monoxide. Like I told you, is going to be the chief reducing agent, and what you're going to get is 2Fe3O4. So 2Fe3O4 plus CO2. Okay, let me just check the balancing here. So iron is balanced, oxygen is 3, fine, 6. Okay, fine. So now the next reaction again is Fe3O4. So a series of reactions keeps happening. Plus 4 carbon monoxide gives 3 Fe plus 4 CO2. Okay, another reaction that also takes place is Fe2O3 plus carbon monoxide gives you 2FeO plus CO2. Okay, so these are the 4 reduction reactions that take place where carbon monoxide is the chief reducing agent. Okay, so what happens after this? Well, what happens after this is very important. It is happening in the hottest part of the blast furnace. So I'm going to write here hottest part. So this is the hottest part. Okay, of the blast furnace where this reaction is taking place. And what is that reaction? So in this part, iron oxide, if there is any kind of iron oxide, so any iron oxide is going to be, I'm sorry, I'm going slow because there's a glitch on my system. So, okay, now it's fine. So any iron oxide that is remaining is going to be reduced by carbon into iron and carbon monoxide. Okay, so this is what is happening in the lowest part of the blast furnace, sorry, which is the hottest part, obviously. Yeah, lowest part and the hottest part. So whatever iron is formed, that's basically going to dissolve a lot of impurities in it, which are carbon, silicon, phosphorus, manganese. Okay, and that iron with all these impurities is going to settle at the base of the furnace, and from there is going to flow out. Okay, so the iron that is collected in this way is going to have a lot of impurities, and this iron is said to be the pig iron. Fine. Now, like I told you, the exhaust gases are obviously going to be carbon dioxide and carbon monoxide, as you found that they were getting formed in the various steps. The carbon dioxide got formed in the combustion zone, then it also got formed in the slag formation zone. The carbon monoxide majorly got formed in the fusion zone. Okay, and if you can just observe from this chart over here, that it is the upper chambers that are having carbon monoxide as the chief reducing agent, and the lower chambers are having carbon as the chief reducing agent. So in the exam, if at all you are asked to identify which are the zones in which the carbon monoxide is going to act as a reducing agent, you always go for the upper chambers, not the lower chambers. Lower chambers will always have carbon that is basically the chief reducing agent, or the coke. Now one more thing to remember, that the melting point of iron is basically around 1500 degrees Celsius. Iron doesn't melt below that. So what happens is, even at 875 Kelvin, even though carbon monoxide is successful in reducing the iron oxide in two places to iron, okay, in the first reaction, I'm just putting a star here, in the first reaction and in the third reaction, you can see there is iron that is getting formed, but this iron is not going to be in the molten state, is going to be in the form of a soft spongy state. Okay, so that iron is going to flow down, is going to come down, and when it reaches the temperature of 1570, that's the fusion zone, if it reaches the fusion zone, it's going to melt and is going to flow down into the bottom of the furnace, and then it will be formed below slag, and it will be collected from the other outlet. So basically this is the whole process of iron extraction, and I've tried to simplify it in the best possible way. So only request to you is that you pause the video and you again see the steps. Okay, revise the different steps and try to write the steps on your own. Okay, or look at the combustion reactions, look at the fusion reaction stage, slag formation reaction, reduction reactions. So look at the different reduction zones, sorry, so look at the different zones and try to remember the reactions taking place in the different zones. Okay, also I'll quickly write down the states for you now, because initially I tried to avoid writing the states. I'll just try to write the states of all the reactants and products very quickly for you. So I've written all the states for you. Also I would like to tell you over here that sometimes it is also mentioned that this reaction which I've mentioned here, the products can also be written in a different way, because see, it is a blast furnace and there are a lot of reactions that are taking place in the blast furnace. So when I have written Fe2O3 plus CO gives you 2Fe3O4 plus CO2, another reaction that can happen in its place could be Fe2O3. So I'm just trying to squeeze in and write here, pardon me for that. So Fe2O3, okay, that can also give you this reaction. So you can get Fe2O3 plus 3CO giving you 2Fe plus 3CO2. So that is also an acceptable product if you write for this reduction reaction. Okay, so see, it's a blast furnace, you never know what is going to combine with what and give what kind of a product. But yes, definitely there are certain acceptable products that are always found in the blast furnace, and based on that all of these reactions are formed. So again, I'm writing the state over here. This is a solid, this is a gas, this is a liquid, and again this is a gas. Okay, so well, that is all in today's video on the extraction of iron with the help of a blast furnace. And I know this might look a lot complicated, but if you keep trying, um, practicing, the process, I'm sure that it won't be that tough. Okay, once you start doing, things will become simpler for you. Fine. So well, that's all in today's video on iron extraction, and if you like watching my video, please do subscribe to my channel. Thank you.